Thank you very much for the introduction, and I would like to thank the scientific committee and organizers for inviting me here. It's a great pleasure and an honor to be here, and really worthy to have come from all over the world from Spain. So I'll go ahead. So this is the contents I will present today. I'll start with a brief introduction of the main types of PVT collector technologies, a global market overview, then some performance enhancement and pathways for collector innovation, the main PVT systems and their applications, some future prospects, some examples of commercial PVT installations, and finally, I'll present the task of the International Energy Agency and Solar Heating Cooling Program. Some of this work is based on two reviewed papers. The main one is this one that was published around 2 years ago with co-authors from all over the world, experts on the field, and then I got also some information from the task of the IEA for some presentations. So photovoltaic thermal technologies appears a promising technology to harvest part of the solar energy that was otherwise lost in PV panels as losses. So PVT converts solar radiation simultaneously into electricity and heat. The temperature level of the heat will depend on the technology, and that will also later on, and then the temperature level of the operation will influence the electricity yield. So higher temperatures will lead to lower electricity yield, so there is a trade-off that will depend on the specific application. So first type is air PVT collectors. The main applications are ventilation and space heating and also preheating purposes. So depending on the channel configuration, as you can see here, there are different ones. The most common one is the channel below the PV panels. Different conclusions have been extracted from the research studies of which configuration is better, mainly because it will depend on the climate and also on the specific application. Overall efficiency is reported at between 30 to 60%, and the most common configurations have a high TRL of 9. There are commercial PVT collectors in the market. Water-based PVT collectors are the fluid is water or a mixture of water and glycol to avoid freezing. They are considered the most efficient PVT technology for preheating water all year long at low latitudes. There are also different configurations depending on where you have the fluid. The most common one is the sheet and tube. And as you can see there as well, there are different designs depending on how you have the flow pattern. Amongst them, the most common is the parallel tubes. There also can be differentiated depending on the number of covers, can be uncovered with 1 or 2 covers, and again, different conclusions have been drawn in the literature, again, because of it depends a lot on the application and the weather conditions. Then we have refrigerant-based PVT, very similar to the previous one, but here the PVT collector acts as the evaporator of the heat pump. So here pretty much you have the thermal absorber attached to the PV, and when the refrigerant evaporates, it cools down the PV cells. There are also different designs, mainly depending on how you have the flow pattern and also the material of the thermal collector. Also, different refrigerants have been used. So here they are 134As commonly used with a similar performance than R12 and R22, but are more environmental friendly, and also R410A is promising. Again, the most common configurations have a high TRL. There are also commercial PVT collectors. And here just an overview of the 3 main configurations you have in commercial PVT. So the first one is a cover collector with a glass and an air gap to minimize thermal losses from the top, and also from behind the exchanger you have thermal insulation. The other alternative is WISC. There is wind and infrared sensitive collector with no cover and no thermal insulation to maximize the exchange also with the ambient. Those two are dominating the market. And the third one is an improved version, let's say, of the previous one that has some fins attached to the fluid current tubes to maximize that exchange with the ambient. That is particularly used for the integration with a heat pump. Then other PVT collectors, there's heat pipe that have high heat transfer rates, or no moving parts, and no energy consumption and long service lifetimes. So the main components are the evaporator and the condenser. There are 2 main types, microchannel flat and cylindrical. They have an anti-freezing ability, so they have better performance in cold regions compared to water-based collectors. And they have a slightly lower TRL, but there are also 1 commercial manufacturers that I know in the market. Then we have dual air-water PVT collectors that can operate in 1 or both operating heating modes. The total efficiencies are around 55% for air and 70% for water heat extraction modes. There are also different configurations, but the most promising one is very similar to the water cover PVT, but instead of thermal insulation, you have some air that can also extract some heat and also acts as a thermal insulation. They have an overall versatility, slightly more complex and expensive than water-based PVT, but the TRL is a bit lower, 6 or 7. So here just a brief overview of some commercial PVT collectors. There are more in the market. I just picked these ones because they have some differences. As you can see, the first one of Avora is covered and insulated, so you achieved low thermal losses, which will be B1. Then while Dualzone and EcoVolt are uncovered, although they have some insulation, so they are cheaper, but at the same time have a bit more thermal losses. And then on the right, you have the Consort. There is a refrigerant-based PVT. It's uncovered, uninsulated with fins. As you can see, it has very high thermal losses, but that is actually looked for because they act as also as the evaporator, a heat pump. And then the Naked Energy one is quite particular. As you can see, they are in a tube. They are like vacuum and insulated, and what they achieve is very, very low thermal losses. Here, there are also some examples of air PVT. I won't enter in detail. This information I got it from Glenn Ryan from Sanovate. He will explain much better than me tomorrow in the industrial workshop the difference between them, but I just wanted to show you that there are commercial PVT as well in the market. Then we have building integrated PVT collectors. So when you install PV in the facade and you mainly use it to produce electricity, then you call it VPV. But when you use that heated air to cover part of the heating demand, then we call it VPVT. So opaque VPVT collectors can be either rooftop or facade integrated. And as you can see there are very different configurations of how to install them. You can find more details there in that review paper. And some of these configurations have a TRL between 7 and 8. There are some also commercial installations. Then there are semi-transparent VPVT that have lower conversion efficiencies, as you can see there in the table. The most common one is glazing collectors with inhomogeneous transparency. You leave the sun pass through the space in between the PV cells. They are also called PV cell clad in VPVT. You can achieve homogeneous semi-transparency with semi-transparent PV cells, typically using thin film encapsulated PV cells, and the homogeneous transparency through frame-integrated PV cells, but here you need a selective coating to reflect towards the PV cell part of the incident radiation. So a bit of the global market overview. So last year, 46 PVT manufacturers reported a bit more than 1.6 million meters square of PVT installed, accounting for 315 megawatts of peak power and 864 megawatts of thermal capacity, out of which 61% was from uncovered PVT collectors, followed by 33% from air PVT, and some 6% of covered PVT. And looking at the breakdown through the world, we see that the vast majority are installed in Europe with a bit more than 1 million meters square, followed by Asia without China, and then China. And as you can see here in Australia, they reported a bit more than 3,600 meters square. And looking in percentage, we see again that Europe has the majority with 65%, and from it, 38% are in France, followed by Germany and the Netherlands. A bit of the global market development. So from 2017, there has been a constant growth of around 80% on average. The highest growth was in 2021 with 13% increase. And last year, the global market increased by 4.3%. And this was mainly due to the strong markets in Europe. Here we see that in Germany and the Netherlands, there was a big increase in the installed capacity. There has also been some interesting developments in China, but the market is still far from the PV sector. In France, the market is still stagnant, mainly due to the collapse of the solar air collectors and also the change in the incentives that led the last year when one of the main PVT manufacturers of air ceased operations. And then in some small countries of Europe, there has been an impressive increase on PVT. Still, these national gains are not sufficient to offset the global market contraction, and the global PVT market is currently in a phase of consolidation and strategic realignment. Looking at the distribution per collector type, we see that last year it's a bit of a mirror from 2022, with 80% of the installed area from uncovered PVT, followed by 17% of covered PVT. And here we see that the air collectors have reappeared the market with 3%. And then looking into the distribution per application area, we see that around 50% are due to solar combi systems in different types of buildings. And then around 20% for domestic hot water purposes and also different type of buildings. So we see that the residential and building integrated applications continue to dominate the market. And now I'll briefly outline the different performance enhancement pathways for collector innovation. You have a lot of details on the review paper that I just mentioned in the introduction, so I just want to give a brief overview. So the first one is collector design modifications. So here the thermal absorber has a very important influence on the thermal performance and on the PV cooling. So we're looking to improve the flow pattern as well as the materials, and then also there has been a lot of research on the use of phase-change materials. Here the selection of the material is very important, and you have to consider the needs, the specific needs, so the ratio of thermal versus electrical energy that you need. There has also been some research lately in the use of aerogels. So the next generation of PV cell technology has also been integrated in PVT collectors. So as you all know here, one interesting way to improve the PV efficiency is to use different solar cell materials to cover different parts of the solar spectrum. So from the perspective of PVT, what we want is a low temperature coefficient of the PV cells. So it is interesting to use a high band gap semiconductor that will leave a lot of photons unabsorbed, which can be used then to be absorbed by thermal absorption. So here, gallium arsenide and cadmium telluride are interesting because they have low temperature coefficients. Another way to improve the solar energy harvest from the sun is to apply some coatings on the absorber surface. And from here, what we use is to minimize the thermal losses to the application of low emissivity coatings, such as the ones we use in energy efficient windows. Here, the material usually used is the transparent conductive oxides or TCOs. Then spectral selectivity is also very interesting to thermally decouple the thermal absorber from the PV cells. So here again, it has to be weighted the ratio of thermal versus electrical energy that you need for the specific use in order to properly design the collector. It also will depend on the climate. So as you can see here, there are different types of spectral splitting. And finally, another way is the use of nanofluids that have been of interest to increase the thermal conductivity of the base fluid. So there are two main options. One is to enhance the heat transfer of the base fluid by adding some nanoparticles. And the other one, nanofluids can also be used to completely alter the optical properties of the fluid, for instance, for direct absorption or for spectral splitting. So there has been a lot of ongoing research, but more is needed. Then going into the applications, as you can see, these are the main applications for the PVTs, and then depending on the type of PVT. So as you can see, liquid-based PVT are the one with more applications. And looking a bit into more detail, we see that the thermal application is relevant for the selection of the PVT technology. So you have on the lower part uncovered PVT collectors that are cheaper, but also due to the lower temperature, they are limited to some of the uses. And as you go to require higher temperatures, you also go to more complex product requirements, therefore increasing the cost. So for water heating, these are the two main options. One is the direct or thermosiphon systems. In here, you don't need a pump, have been widely studied because of the elimination of the circulation pump saves both investment cost electricity. You heat up the water in the PVT collector that goes directly to the thermal storage tank to provide the hot water demand. It's a good option in warm climate applications. Instead, another option is indirect systems in which you have a closed loop of the PVT collector, in which you usually use water, sometimes with antifreeze to avoid the freezing. These are more expensive and usually have longer payback times than direct systems, but usually have also higher efficiency and more versatility. Here, the operating conditions can be controlled and optimized with more flexibility than direct systems. And this is a typical example of a configuration of liquid-based PVT for water and space heating. So there are three main circuits. You have the primary solar circuit that I was mentioning is a closed loop that heats up water in a storage tank. And then you have the secondary circuit, which will be demand, for instance, an open loop for the hot water or the space heating in a closed loop. Previous research estimated payback times between 12 to 15 years in Mediterranean countries, while if you go to low solar irradiance and low ambient temperature countries, the payback is a bit higher, around 20 years. Again, usually these systems are more complex than air-based PVT, but they also have higher efficiency, better versatility, and also more compact. So another option is to integrate liquid-based PVT with a heat pump for space heating. First option is the direct solar-assisted heat pump systems. In here, you use a refrigerant-based PVT that acts as the heat pump evaporator. The energy output increased from the condenser, so you have a higher heat pump coefficient of performance. But using the PVT as a heat source of the heat pump places special demands on the heat pump. For instance, it has to cope with highly fluctuating temperatures from the brine that comes from the solar circuit, and it can also have to withstand higher temperatures in summer months as well as very, very low temperatures in winter. So the approved range of inlet temperatures for the heat source for the heat pump is a very critical criterion in order to select the heat pump. So not all the heat pumps can be used with PVT as a heat source. Then we have indirect systems in which you have, again, like there are different separated loops. Here you can use water-based or antifreeze plus water PVT collectors. There are different designs of the different type of PVT collectors that you can use. Usually they are more expensive and longer payback times than direct systems, so they are recommended in larger applications. And as you can see here, there are different configurations depending on how you integrate the solar loop with the heat pumps. You can also use different types of heat pump, and the most appropriate and efficient configuration will depend on the specific application and also on the boundary conditions. Usually you use water or refrigerant base, but then you can also use heat pipe PVT collectors. And then air-based PVT can also be used to provide space heating. So there are two main configurations. First one is to integrate them with a heat recovery unit. So here you can use the hot air from the air PVT to directly supply the heating demand, or to preheat the air to a heat recovery unit. And previous research estimated efficiencies, increasing efficiencies of 20%. You will need also additional dampers and connecting that work. Another option is to integrate them with an air source heat pump. In here, you use a mix of the preheated air from the PVT together with the ventilation exhaust air as the source of an air source heat pump. It improves the heat pump coefficient, and its previous research estimated there is a reduction in electricity consumption by around 20% in winter. You can also use PVT to provide as well, so domestic hot water, space heating, electricity, and cooling. So for this, you have to you provide a cooling technology. In this case, there was integration with an absorption chiller. It needs an auxiliary heating system to provide heat when the PVT is not enough. And here, the cost competitiveness is highly dependent on the utility prices, and you may also need some economic incentives as the price is higher, especially because of the high price of the absorption chiller. Another way to provide also cooling is to integrate water-based systems within an indirect system, and thermal storage tank with an air-to-water reversible heat pump. So here you make use of on-cover PVT collectors and the radiative cooling. So at night, it will cool down the PVT collectors will cool down the water, and you store in an inertia tank, and during the day, it will heat up the water to provide space heating. So here, the system performance will depend on the demand and climatic conditions and also utility prices. So some future prospects. So here you can see the price development of PVT collectors in the last 4 years. I got this from this European project, Integrate XL. So as you can see, it decreased slightly between -4 and -9%, depending on the PVT collector type. And here you can see an example of estimated cost breakdown for a residential PVT installation. So you see that the PVT collector are less than 50%, and the PVT system cost will increase with the complexity. So as you go adding more auxiliaries and more control, the price will increase. So some challenges for adoption. Further research is needed on the integration of PVT system in the distribution grid, life cycle assessment, retail economic analysis, and environmental analysis. Due to the limited maturity of this technology, there is a lack of studies on long-term reliability. So it's more needed to assess it. The cost still considerably larger than for PV and solar thermal collectors. The cost is expected to decrease with the wider installation of the PVT thanks to the economies of scale. The general public installers are still not aware of their existence, the efficiency of the high performance. This has been one of the main motivations of the new task. Also, there is no specific norm for testing PVT collectors, and it is needed to compare different technologies available in the market. So summarizing, the main bottlenecks include higher price, public awareness, product standardization, warranties, and performance certification, as well as more installation and training experiences. So some potential pathways for improvements of PVT collectors include the enhancement of the PVT collector performance through the modification of the thermal absorber to increase the heat transfer area, and also the use of selective coatings by developing cost-effective methods to integrate them in the absorber surface. Also, in integrating PCMs in PVT collectors, including the addition of nanoparticles to improve the thermal electrical efficiencies and also improve cost competitiveness. Also, more research in nanofluids in PVT collectors, analyzing the life cycle, the stability, and environmental impact. Holographic filters are promising, but more scale-up demonstrations are needed to prove stability, reliability, and performance, as well as viable mechanisms to reduce the cost of production. Luminescent concentrators could have the potential to further development in PVT collectors, but more research is needed there as well. And finally, optical absorption of nanofluids to demonstrate the potential when the actual flow in the fluid filter generating useful energy. So more research is needed on new and cost-competitive products, recognized testing and procedures and standards, as well as demonstration projects. There is a need, as mentioned, to improve the electrical and thermal performance of liquid PET, particularly on the thermal absorber design and fabrication. It's critical, the lamination to the PV module, as well as the heat exchanger design, material and coating selection, energy conversion, and effectiveness, performance testing, optimization of contact between the electrical and thermal power system optimization, as well as thermomechanical stress and reliability. We will need to make use of the rapid prototyping, the finite element and CFD methods will allow to fasten the PVT development and also reduce development costs. And then finally, there has been a lot of ongoing research in solar cooling, but very little considered PVT as a potential driver of solar cooling. So if a scalable and cost-effective PVT can be developed, then solar cooling is an area of low-hanging fruit where we could be beneficially employed. Here's just some overview of different PVT installations. I will give more details tomorrow in the industrial workshop, but just to show you that they can be used in different type of buildings, such as residential, hotel, hospitals, and also for domestic hot water preheating or for space heating. Here there are other examples of the integration of PVT with heat pumps or with geothermal energy with boreholes. A bit of reality. So lately there has been a lot of research. So as you saw, last year there were more than 12,000 research articles and reviews published on PVT. But then you look at the area installed, you see that there is almost one article per 6 meters squared of newly installed area. So it is great that we have a lot of ongoing research, but we have to boost the PVT installations. And this has been one of the main motivations of the task of 73 of the International Energy Agency and the Solar Heating and Cooling Program. Here you can see the leadership team. So the task leader is Dr. Convener Kramer from Fraunhofer. We have sub-task leaders, as you see, from all over the world. We have Doug Smith from here, from Australia. I'm also leading a sub-task. So key objectives are to create a factful awareness about PVT heating systems, identify and tackle hurdles in innovation systems around PVT, as well as foster and activate the industry and research community on PVT, and more importantly, to initiate and multiply PVT heating installations. So the task is divided in 4 subtasks. The first 2 are for liquid heating and air heating, respectively. They aim to gather concepts from product level to system level, as well as various market applications. Then we have 2 transversal subtasks that are awareness and policy, including how to talk about PVT, providing facts in infographics, and explaining complex systems with simplicity. And then finally, we have the modeling and monitoring, which is the one I'm co-leading, that we aim to address how to simulate solar-assisted heating PVT, filling methodology gaps, as well as provide some field installation monitoring and transfer to the market. So here you can see an overview of the task interested parties. So as you can see, there are a lot of in Europe, but you still have some interested parties from Australia and Asia. And I hope that after this conference, we have more interested parties from this part of the world. So thank you very much. Any question?
Thanks, Maria. So do we have any questions from the floor? One in the back corner. Up there.
Yes. Hey, Maria. Thank you. My name is Omar from UNSW. So I have two questions. The first one is about the PVT efficiency. What I've noticed when we're doing this experimental data is that the efficiency is very sensitive to wind, so heat losses by wind. So I'm wondering those efficiencies that you showed in one of your slides, does that take into account wind somehow? And my second question, it seems to me with the PVT, they become more efficient only when we start complicating the system by having multiple storage tanks, a heat pump, a fancy control loop. So I was wondering if there's any work out there on how to simplify all of this and reduce the amount of moving components in a PVT system. Thank you.
Thank you. So answering your first question, yes, wind, it influences a lot. That's why some manufacturers went to cover PVT. This way you have less influence, but then they are more expensive. So I don't know exactly which figure you mentioned, but those are average. So again, the thermal efficiency will depend a lot on the type of PVT and also on the application. So if you make it work at higher temperatures or at lower temperatures, even on the conditions, it's not the same when you have, I don't know, here that in the other side of, even from Australia. And looking at answering the second one, yes, that one of the issues is that you can get very fancy and very efficient systems, but then you have to add, as was mentioned, several tanks, and then you have this heat pump helping, and then you get the price increase. So there is not a perfect solution. So what I've seen from the installations is that at the end of the day, they go for, let's say, more simple installations, even though they are not so efficient, because when you go into the economics, then it's better that even if you reduce a bit the efficiency, the cost is lower. So at the end, you have lower payback times, which is what people at the end ask, like, how much time do I need to recover my investment? That's the question that everyone asks at the end, not into the efficiency, but the money.
I might, if there aren't any other questions, we might leave it at one because, oh, Ken, yes?
Thank you. Thanks, Maria, for a great presentation. I was wondering, are there any issues of electrical safety by having PVT where you've got a fluid that may be a conducting fluid quite close to the PV, or are you relying on the PV manufacturer for that?
Yes, so between the PV cells and the thermal absorber, there are several layers that try to avoid that potential conductivity. So you have like 5 of them, you have some blue, you have some EVA, so you avoid that, and yes, at the end you trust on the PV manufacturer, make sure that there are not losses, leakages of electricity, and then those layers in between will prevent it.
Okay, if it's okay, I might leave it at that because we're going to run short of time, but Maria will be here for days, and if anybody's interested in that work, talk to Maria, but if you're interested in the tasks, then you can talk to Maria or to Ken Guthrie around the solar heating and cooling tasks. Thank you very much, Maria. Join me in thanking Maria.